Welcome to the pre-recording of lecture 18, scheduled for the start of week 7 in our 8-week summer course. So in this next to last week, we start to look at harder problems for which we will show that there is no polynomial time algorithm. So we will start by making the concept of polynomial time reductions um, formally by means of several important examples. In the second half of this lecture, in the next pre-recording, we will address the satisfiability problem. Okay, what did we do last week? Well, we considered network flow, and in particular, we showed that the algorithm of Ford-Fulkerson, an iterative algorithm, provides provides efficient algorithms for a whole range of seemingly very different problems. So we looked at the definition of the Ford-Fulkerson algorithm. In the next lecture after that, we considered bipartite matching and circulation with demands. And then in the lecture 17, we considered the edge disjoint path, survey design, and airline scheduling. In some sense, these are all very different problems, but they all have the same answer. So you can actually say that if you know the Ford-Fulkerson algorithm and you understand the problem of network flow, they are actually all solvable efficiently by the Ford-Fulkerson algorithm. So that's a very good strategy to solve problems. So you have a good algorithm, so you have a good implementation of that as well. And then you reduce the input of other problems to that problem for which you have a good implementation. Now we're going to do the same thing now in the remainder of the course, but now we are going to do this for computationally hard problems, showing that there is a whole connection between problems if you can solve one problem efficiently, or if you would be able to solve one problem efficiently, then you can solve a whole class of problems efficiently. Okay, so I like this cartoon a lot, and also with this cartoon I like to introduce the literature. So there is the classical book of Gary and Johnson. So graduate students are taking this course. A goal of the course is also that the literature becomes more open to you, not only our textbook. So here is then the question. So some situation that you will never would like to find yourself in. So I can't find an efficient algorithm. It just means that I'm just might be too dumb. Well, actually, what you want to say is that there isn't such algorithm possible. Now, if you say a statement like that, then you probably say this as a young person to a more senior person, then you should actually say that even if you can't prove, then there is a whole range of other people who worked on this problem for a very long time and also couldn't really solve it. In some sense, that is the motivation to what we are doing. We are going to show that there is a technique to show the equivalence between problems. Okay, this technique is essentially a rewriting technique or a reformulation of a problem, and it is important that these formulations happens in polynomial time. So if we can reformulate the input to problem X into problem Y, then if we can solve Y efficiently, then we can also solve X efficiently. So, and it doesn't really matter then anymore how we can solve y. So here it is denoted now differently. I didn't look at the slides when I was telling the story. Assuming we do have an efficient implementation to solve x, so it's called a black box. We don't really know, we don't really care even how it is solved. It's only it is capable of solving it. Um, if y is polynomial time reducible, so that means that any instance of the input of y can be translated into an input for x in a polynomial number of standard computational steps. That means in the terminology of this course that there is an efficient algorithm which scales very well asymptotically. So the input of y can grow arbitrarily large. The number of steps, and they are standard basic computational steps that you need to do to reformulate y into an input for x, then actually you can solve it. We actually allow not only one call, but also a polynomial number of calls to the black box solver that solves the problem. So it is more general than what we did last time. Last time we always solved one network for formal network flow problem. Here we will be allowing polynomial reducible that you have to solve the problems in a loop. If you have a finite number or a polynomial time number of calls to the black box solver, that is perfectly fine. So that's the notion of polynomial time reducible. So I said the input, but of course the instances also concern the output. So you can formulate the input of y to an input x, and the output of x can also be formulated into output for y in polynomial time. That is what it means to reformulate a problem. Okay, here is now the consequence. If you can solve x in polynomial time, so you run your black box, then if y is polynomial time reducible to x, then also y can be solved in polynomial time. Okay, if so in some sense this proposition and this proof is interesting to recapitulate the definition of the previous slide, which slided by. So the notation y polynomial time reducible to x means that you call a polynomial number of standard computational steps to reformulate the input of y into the input of x, and the output of x is also reformulated into the output of y in polynomial time. This all runs efficiently. And also you have a number of black box solves to call that actually solves the problem. Okay, then how can you be solving the problem in polynomial time? Well, you first solve the problem x in polynomial time, and you then call a number of times to the black box solver. If that runs in polynomial time, so you have a polynomial in the running time of your black box solver. So there is the property that the composition of two polynomials is again a polynomial. And you have to add, so that's the cost of the calls to the black box solver. And then to that you have to add the cost of the formulation. And that's the formulation of the input and the output. And therefore you can solve the problem y also in polynomial time. Okay, so that's very practical. Now let's go to more difficult problems. So the problems that we have covered so far in this course are all computational tractable because we had efficient algorithms to solve them. If we do not have polynomial time algorithm, then we say that the problem is not computational tractable, or for short, intractable. Now, if a problem cannot be solved in polynomial time and y is reducible to that problem, then also y cannot be solved in polynomial time. So this is an important statement. And the proof of it is simply by contradiction, by contraposition. So contraposition means that if you have an if-then statement, you negate the then. So if y cannot be solved, can be solved in polynomial time, so not means can. If you have y that can be solved in polynomial time, then you can also solve x in polynomial time. So that is what the contraposition does. The statement is important because even the proof showing that that you don't have an efficient algorithm, it may help you to reformulate the problem. Because as soon as you would find an efficient algorithm, you would find an efficient algorithm for a whole class of problems. Okay, so let's now look at an example. We have introduced terminology. So the first example is an independent set problem. So if we have a graph defined by vertices and edges, then a subset of the vertex set is independent if for all the elements in the set there is no edge. You can look this, if you here you see an example, you have 7 vertices, so you could see this as a social network. And the people who do not, for which there is no connection to, they do not depend on each other. So there is no social interactions between any of the people in this independent set. So here you see an independent set highlighted by a set of 4 vertices. So these are 4 vertices in the interpretation of a social network. If this graphs in between 7 people encodes their relationships, if they do have a relationship to each other, then you have 4 of those 7 people who are independent of each other. If you are organizing a party, for example, for 7 people, so then there are 4 of them. If they would be together, then they would make a group of 4 people who do not mutually know each other. Okay, finding an independent set can be done by an exhaustive search, and dynamic programming applies to organize an exhaustive search. So here is the relationship between the complete problem and the sub-problem. So you take your graph and some vertex. Now, and then you reduce the problem to removing that vertex from the graph, which means removing it from the vertex set, and also removing all the edges that contain that vertex. So there is G prime that is now completely disconnected from the vertex V. So if you find an independent set in that graph, can you G prime, can you actually use that connection to derive a recurrence? So if you are removing that vertex and all the edges, so you find an independent set then in that graph, can you actually find this efficiently? So the recurrence here assumes that it would work, so you would reduce the problem with n vertices to a problem of n minus 1 vertices. But the problem might still be that the combination step might actually give you still problems. Um, try to organize an exhaustive search and what is the running time. So you should find something that is exponential in n. Um, so notice here, if you think about this, if you are starting with the first vertex, you remove it, then it's indeed true that 4, 5, 6 are an independent set of three elements. But since you removed the connections here, so you went from a graph of size 7 to size 6, that's the obvious reduction here, then nothing prevents you actually to pick the vertices 2 and 3. So one needs to be a bit clever about setting up the exhaustive search, otherwise the combination might not work. So it's okay to actually consider all the vertices. So like in the reduction, you can actually call. Um, if you would have a polynomial time algorithm for the independent set problem, then if you have it for n minus 1 vertices, you could show that you also would have it for n vertices. So um, we are considering intractable problems. That word intractable sounds often a little bit discouraging, but intractable problems are often also very interesting problems. So that doesn't mean that they are not worth solving. So here, consider running, um, providing essentially defining the algorithm for a solution for this problem. And what is then the running time of this algorithm? Okay, so we have formulated the independent set problem as actually a decision question. If you have a set of seven people with their relationships defined by the edges, or is it a subset of four people, of four persons, of four individuals that do not know each other? So you could alternatively essentially ask for, given any graph, what is the largest independent set? So if you consider the notion of polynomial time solvability, then actually both problems are equivalent. So in some sense, the polynomial time reducibility actually resolves us, gives us a lot more flexibility because we can use efficient algorithms to reformulate problems. So how can you reduce um, a decision problem to an optimization problem? Well, consider again the example. You could work with, you can solve your decision question by, in the graph, say with seven people, you first check whether there is something for 4, and then if not, there is no independent set of size 4, well, then you check for size 2. Otherwise, you look for, say, size 5 or 6. So you do a binary search. So you can solve a polynomial time number, and here logarithm runs very slow, almost constant. So you can solve a number of optimization problems to solve the decision problem. Decision questions are more convenient to work with. So you have a yes or a no answer. Um, but just like with running any algorithm, there are solutions, there are certificates. So the optimization problems would actually provide the certificates to back up your answer. Uh, if there is no such answer, you could also say that you solved your optimization problem and there was no such value for, there was no independent set of size k because we found that the optimal number was less than k. So that would be the certificate where you would back up your yes or no answer. So the bottom line is that you can reduce decision questions to optimization questions in polynomial time. Okay, so let's consider another problem. Again, given a graph, vertex set and edge set, we now consider the vertex cover problem. A vertex cover is a subset of the set of vertices such that for any edge that you have, either or both, either you have that the first vertex in the edge or the second vertex or of S is actually contained in that set. It's not, the or here is not an exclusive or. So you can have edges that contain both their endpoints in the set. Okay, here is our graph again. So you can again see this as a graph of a social network of 7 people, and you want to know what is the minimum set of people who actually, what is the minimum size, or here you see that there are 3 people who actually, if you take those 3, they know in total, so they have relationships with all other people. So this could have practical implications as well. Finding a vertex cover in a graph also actually implies that if you have that set, then you can actually reach all vertices in the graph in one step. So this is an important notion, that of a vertex cover. And again, the same exercise. Compute a vertex cover. In some sense, this is an invitation to ask for an efficient algorithm, and we can apply dynamic programming to this. So given on input a graph and a vertex, we can reduce this question to computing a vertex cover to a smaller graph just by removing that vertex and also all the edges that contain. So this would lead to an algorithm. So the purpose of the exercise is that you describe the algorithm in sufficient detail to derive the running time of the algorithm. And again, this running time should actually not be polynomial in the input size. Okay, 2 different problems, the independent set and the vertex cover. Now, if you can solve one problem, you can also solve the other. So here I picked the same example, and you see the solution to the independent set. So these are the people in a network of 7 who do not know each other. Then it turns out that the complement of that set of people, so these are 4 people, 1, 4, 5, 6, who do not know each other. It turns out that if you take the complement of that set, so you take the 3 people from those 7 who are not in the independent set, then actually they are defining a vertex cover. So the first two exercises ask you to uh, define algorithms, and if there is would be a homework collection, if you can solve one of the exercises, you can solve the other exercise. And that's also actually the whole point of this equivalence relationship here. If you have a good implementation of, say, an algorithm that solves a problem, then it pays off to work on efficient rewritings of the inputs and the outputs. Okay, but so here on an example, it's obvious that if you have solved the independent set problem, you can also, for this example, you have solved the vertex cover, and also taking the complement is easy. So, but this is on an example. This is actually hold in general. Well, that requires a theorem or a proof. So we formally repeat the definitions of a vertex cover and an independent set. So if we have a graph, then if we have an independent set, then we also have a vertex cover. And if we have a vertex cover, then also we have an independent set. So this is an if and only if statement. So the two problems are equivalent. So we're going to show that if we have an independent set, if we consider any edge, that means that the vertices, which are not connected, be an edge. So these two are independent. So both u and v cannot be in that independent set. So what does that mean is that if you have an independent set, that means that u or v must be both in the complement. So that means that if you take the complement of an independent set, then actually you do have a vertex cover. So that edge that you picked has at least one vertex. Okay, the other way around. So if you have a vertex cover, then you also have an independent set. Well, take again. So we have a vertex cover, and now this is denoted by the complement. So if you actually are given the complement, so if you now take the complement of that, that is the S. So, and you note that since they are not in the vertex cover, if you take the complement, they are not part of that. So if you take the edge between two of them, then actually you actually find that all the edges that you can make, those u and the v, they must actually be independent. So by taking the complement, actually you find the vertices that are independent from each other, for which there is no edge. So that's actually what the proof does. If you have your vertex cover, you look at two edges in the complement, two vertices in the complement. If there would be an edge between each other, they would not be in the vertex cover. So there is no edge between them, so they are part of the independent set. So the proofs actually work by contradiction. And I should also have said that this was also approved by contradiction in the previous part. Okay, I hope this was clear. So since these two problems are equivalent, then it means that they can be reduced to each other. So independent set can be reduced in polynomial time to vertex cover. So if we have a black box solver then for the vertex cover, then whether we have a graph that has an independent set of size at least k, can be decided by asking the black box solver where the graph has a vertex cover of at most n minus k. So the decision problems, if you have a black box solver, a size, so because we have the complement, size k becomes size n minus k. And of course, obviously, which is not stated here, taking the complements runs in linear time. Okay, so also the vertex cover reduces to the independent set. So if you have an independent set, so the proof of this consequence is entirely symmetrical. So if vertex cover reduces in polynomial time by independent set, then if you have a black box solver for the independent set problem, then you just have to take the complement size of the k where you're working with. And that is the same as asking if you're interested for a vertex cover of size k, if you have an independent set of size n minus k. Okay, let's now show some more illustrations how this can uh, applied. So there is kind of a equivalence between these two. So if you want to consider independent set problems, then you can see this as a packing problem. Um, so we want to actually often find the largest independent set. So we're also avoiding now the edges. You could also say that these are the conflicts that are avoiding. Um, so now thinking again about social problems, if you are organizing a dinner party, so you probably do not want to seat people next to each other or in close proximity to each other um, who are in conflict with each other. So these packing problems, they do have practical real life applications. A vertex set problem is naturally viewed of a covering problem. So I mentioned that if you have a vertex cover, in some sense this is already a reduction of the graph. This is a subset of vertices through which you can reach all the other vertices in just one step. And actually, this also translates then in the number of edges that you have to select. Um, so it's a little bit similar to the computation of a spanning tree. And again, you may be wondering why wouldn't there be an efficient implementation for this? Well, perhaps you found a shortcut in the last exercise. Um, so here vertex cover is a special instance of the set cover problem. So we're going to try to generalize the vertex cover problem, um, which is now stated here. So if you have a number of items, then you want to, and a collection of subsets and a number. Now, if there then a collection of, if there is a selection of these collections so that you can cover the entire set. So you have U, you could interpret this as the universe, and then you have a finite number of subsets. So M could be all subsets, but typically it is a finite number. You want to decide if there is a selection of these subsets that covers the entire set. So vertex cover, there you have actually, you're looking actually then as the edges in the graph. So is there um, so for edges, you actually are considering the pairs of the vertices. So you, here we actually consider many edges, so collections of edges. So I hope it is clear that the set cover uh, generalizes the vertex cover. Okay, what is an application or an illustration of the set cover problem? Assume that you have a number of capabilities that you want to cover. So there are certain tasks that you need to be able to do, and you have software packages that have the capabilities for those tasks. So here we have 10 capabilities, and we have many software packages to choose from. So all these software packages are represented by either the ellipses or the big polyhedral polygon shapes. And the question is to make a selection of your software systems so that you can cover all your capabilities. So here you see in the example we have 10 capabilities, and we can find 3 software systems that cover all capabilities. So there is some overlap, there is some redundancy, but you cover everything. So, and if you count now, I have in the set cover 3, but I had 4 more uh, software systems. So I had a total of 7 software systems, but I only needed 3 of them that cover all the capabilities. Okay, so this is an application of the set cover problem. We will show that the vertex cover reduces in polynomial time to the set cover. So how do we prove this? So we can see the vertex cover as a graph of vertices and edges. And suppose that we now have a black box solver for the set cover. Then how do we define the inputs for our black box solver? Well, the universe is the set of edges, and all the subsets are the edges that are containing every vertex. So the size of every subset equals the degree of the vertex. So we have n vertices, and then we have as many subsets. Okay, I will illustrate. So this is a general proof, but let me illustrate what this construction does. So I have my graph, the running example in this lecture, 7 vertices. So I have my edges, so which is now denoted as the universe. And then I have all these subsets. So you can see that S1 is the collection of all pairs where 1 is contained in one of the elements of the pairs. S2, so S2 has degree 4, so that set S2 has cardinality 4, etc. I have 7 subsets for the 7 vertices. So this is how you set up the input for the set cover. Okay, the set cover problem, we can set up so for the capabilities. So we have the edges. The edges are now representing um, the capabilities. So you can see that I have 10 edges, so they are arranged systematically. So you can see the coordinates of these edges um, arranged. So we have the subsets which correspond essentially to the vertices. So the vertices that are contained in these edges. So if we have a subset of the sets, and so we have now the question is, can we cover all the edges. How many subsets do we need? Well, it turns out that we need 3. Okay, and the number 3 was also the number of vertices that actually covered the graph. So you can see there is a one-to-one correspondence between the set cover. So we have the sets that cover all the edges. So we have 10 edges. So it turns out that 3 subsets suffice to cover all of them. While we also have 3 vertices. There is an independent set of size 3 in this graph. So there is a one-to-one correspondence between the set cover. If you can solve the set cover, then actually you can also solve the vertex cover. So this is to illustrate this proof here that any instance of the vertex cover you can actually reduce to the set cover. It's a polynomial time reduction, so you simply you copy all the edges, and then you collect in the set all the edges that are incident to the vertex. So in a way, if you remember the edge list representation of the graph, the sets Si actually correspond directly to the lists in that array of lists. Okay, now let's finish that proof by the lemma. So if we have a solution to the set cover problem, so that's actually the first statement in this lemma, we have found k sets of the subsets. We have m edges. I'm sorry, so we have m subsets. It doesn't really mean here the m is a little bit confusing to me now. So we can at most k of the sets. So if we have a solution to the set cover problem, then actually we have also solved the vertex cover problem. So this formalizes this here. So we have the sets. If they cover, then actually it means that in these sets every edge is incident to these vertices. So you can essentially read off what the vertex is. So you can take actually the intersection of all the edges, for example. So that actually gives you the vertex cover. So if you actually have the vertex cover, then you know which sets to take, because the index in the vertex, the name of the vertex in the vertex cover, is actually the index to the set. So in some sense, this lemma seems to be just translating the statements. So the numerical example, in some sense, make this clear. Okay, now we have the statement of the theorem. So there are two QEDs on this. So we have the first QED from the lemma, and then there are the graphs that are being used to translate in linear time, essentially, the input to the vertex cover to the input to the set cover. Then we call the black box solver for the set cover. And then if there is indeed, the black box solver will also produce for you all the sets. Then if that answer is yes, then we have answered also the vertex cover. Okay, we had said that the set packing problem is actually the independent set problem. We started with that problem. That's actually an instance of a packing problem. So we can also formulate a more general version of the independent set problem, where we have a collection of subsets, but now instead of covering everything, we want a collection, the largest collection, or a collection of size k. So again, the decision problem and the optimization problems are equivalent upon polynomial reducibility. So we want to ask if there is a collection so that none of those two intersect. Okay, so this is an application. We can go a little bit faster here. So we have a set of um, resources now that cannot be shared. So if you think about, it's not so much good to think about um, capabilities now, but you can think of resources that you can't share. Can you actually have a subset, a selection of subsets so that there are no intersections? So you can see this. So here I should probably properly explain what is on the slides. So you could see these resources that are necessarily to run some processes. So the processes have to use some of the resources, and while the processes are using those resources, other processes cannot be utilizing those resources. So this could be seen as an application of a scheduling problem, and it has implications for example, parallel tasks that you want to run at the same time. So the application is that how many processes can you run if all these resources are up at the same time, but they can be utilized by only one process. Okay, so here is the exercise. Show that you can solve independent set by the set packing. So look at the example again. So you have to work this out for the example of the of the graph of 7 problems. Formulate the set U and explain how you can go from the set packing problem to the independent set problem. Okay, so that's the end of the first part, where we introduced the independent set and the vertex cover. We demonstrated that if you can solve one of them, then you can solve the other. Can you solve the other, then you can solve the first. We have generalized the vertex cover to set cover. And as an exercise, you can also generalize the independent set to the packing problem. In the next lecture, we will consider other problems that are reducible to each other.